and strain. And why does a neutral axis form? Within a bent beam, there is a neutral axis where material experiences no tensile or compressive stress, acting as the equilibrium point. How is stress distributed? Stress varies linearly from the neutral axis with minimum compressive stress on the concave side and maximum tensile stress on the convex side. Theory of uniform bending in this picture shows constant bending moment. Applied forces create a pure couple leading to uniform curvature. And circular arc deflection, the beam deforms into a perfect arc of a circle. Simplifying analysis. And uniform bending equations and experimental setups of Young's modulus y is equal to mgl divided by 4I into y2 minus y1, where m is equal to mass, g is equal to acceleration due to gravity, L it's equal to length between knife edges, and I it's equal to moment of inertia, y2 minus y1 it's equal to deflection difference. In the experimental setup typically involves supporting the beam on two knife edges and applying equal weights at points equidistant from these supports. The central portion of the beam undergoes uniform bending. Theory of non-uniform bending, like as varying bending moment, the bending moment changes along the beam's length, leading to a non-uniform curvature. Parabolic deflection, the deflection curve is typically parabolic, more complex than uniform bending. And non-uniform bending equations and the experimental setups of y is equal to mgl cube divided by 4bd cube into delta. M is like as mass, G like as acceleration, L like as length, and B like as breadth of beam, D like as depth of beam, and delta like as a central depressions. In a typical non-uniform bending experiment, the beam is supported at its ends and a load is applied at its center. The deflection is measured at the point of load applications, like as to in the image shows. In experimental procedure and observations of measure dimensions, accurately measure beam length, breadth, and depth using a vernier caliper and meter scale. Record of deflections like as uniform bending, record deflection at 2 points for non-uniform, record central depressions. Applying load incrementally like as place known weight onto the loading pan and record the corresponding deflection using a spirometer or traveling microscope. Plot and analysis of uniform and non-uniform bending like as deflection graphs use the slope to calculate Young's modulus. And in this graph shows the uniform bending deflections, it's improved to gradually, like as a calculations of deflections curve. And non-uniform bending like as improved the same ratio. So these two different parameters like as the deflection of the uniform and non-uniform bending. And applications of Young's modulus, like a structural engineering, designing bridges, buildings, and other structures to withstand loads without excessive deformation. Biomedical devices liking as developing implants and prosthetic with mechanical property similar to natural tissues. And like as a aerospace designing, like as selecting material for aircraft components that are both strong and lightweight materials and preventing critical failures. And material sciences characterizing new materials and predicting their elastic behavior under stress, like as automobile, car, bus, and bike transportations materials. In these materials of structural engineering, we have designing a bridges, pillars, and jointing of pillars and buildings like as beam and roof of the building and floor of the building like all of us Young's modulus structural methods. In biomedical devices, we can implementing lot of places in the uniform and non-uniform bending like as physiotherapy medical services like as traction method and aerospace designing like as wings and other aerospace designing work nature. Thank you. Thank you guys.